Now that we learned about link layer, Ethernet, LANs, and virtual LANs, it is an appropriate time to take a look at MPLS, which is said to be networking at layer 2.5. Let's take a brief look to find out what that means. Multi-protocol label switching, or MPLS, is defined in RFCs 3031 and 3032. It is a technology with an initial goal of increased speed of forwarding. For this purpose, it uses a fixed length identifier, which is known as label. It uses it for forwarding purposes. This removes the complexity of forwarding compared to IP-based shortest prefix matching and enables faster forwarding of packets based on fixed length label. The initial idea used in MPLS comes from circuit-switched telephone network, evolving to a packet-switched virtual circuit. To support MPLS, the Ethernet frame is extended to include an MPLS header. This header includes a label, 3 bits for experimental use, an S bit for advanced use of announcing the end of stacked MPLS headers, and a time to live field. The IP datagram remains unchanged. An MPLS-capable router, which is also called a label switch router, can perform switching based on the MPLS label only. This means that it forwards packets to the outgoing interface, deciding only based on the MPLS label value. For this purpose, it will not inspect IP address. MPLS forwarding table is distinct from the IP forwarding table, and the forwarding decisions might be completely different. It can use destination and source addresses together to route flows to the same destination in a different way. Remember that not being able to support this was a concern in destination-based forwarding. MPLS also has the capacity to reroute the flows very quickly through a new path to the destination. This is done if there is a problem in the current route and is enabled through pre-computing backup paths. This will need a way like routing to find the paths, as well as protocols to distribute the MPLS labels to be used for switching. Current routing protocols like OSPF are extended with support for flooding information to MPLS-capable routers. Other protocols like LDP or Label Distribution Protocol and RSVPTE are also used throughout this process. In destination-based IP routing, path to destination is determined by destination address only. However, using MPLS routing, path to the destination can be based on source and destination addresses. In that sense, it enables different flows of traffic to follow different paths and enables traffic engineering. For example, in the figure, IP MPLS entry router R4 can use different MPLS routes to A based on, for example, IP source address or other fields. The process of using an alternative path in case of link failure is enhanced using a mechanism called fast reroute. The pre-computed paths that are stored in the MPLS-capable routers are used for this purpose. To enable these properties, OSPF, ISIS, and other routing protocols are extended to include MPLS routing information. This could include information like link bandwidth, amount of reserved link bandwidth, and other required information for MPLS-enabled routers. For example, routers R1, R3, and R2 can let other MPLS-enabled routers know about their available bandwidth. Namely, if R4 wants to route something to A using MPLS, at the first step, it needs to be informed by R1, R2, and R3 about the reachability and available link bandwidths on the path to to A. In addition, protocols like RSVP-TE signaling could be used to set up the MPLS forwarding. To do this, the entry MPLS router uses RSVP-TE to set up MPLS forwarding at the downstream routers. For example, R4, the entry router here, knowing the reachability and available bandwidth from other routers, can set up a switch path towards A. Let's expand a little bit on the same example. Routers R1 to R4 are MPLS capable. Routers R5 and R6 are standard IP routers. We want to route packets from R6 towards destination A, which is connected to router R1. R1 has advertised to R2 and R3 that R1 can route to destination A, and that if it receives a frame with an MPLS label 6, it will forward it to destination A. Router 3, in a similar way, has advertised to router R4 that it can route to destination A and D, and that it will forward the labels coming in with MPLS label value 10 towards destination A, and incoming frames with MPLS value 12 towards destination D. Router R2 also has advertised to R4 that it can route to destination A, and that if it receives a frame with an MPLS label 8, it will forward it to destination A. R4 can now choose any of routers R3 or R2 to send packets towards destination A. It can use one of these paths as the main path and the other as the backup path used in fast reroute.